So today we are moving on to 9.1. You'll see at the top there where it says an infinite series. Seems trivial, but the word series is kind of important to understand. And we want to contrast that versus what we would have done yesterday, which was an infinite sequence. Because they're similar, yet in one big way they're going to be different. Okay, so an infinite sequence or infinite series is an expression of this form. So you have your first term, second term, third term, fourth term, your nth term, on and on and on and on and on. The difference being, when it was a sequence yesterday, all we were doing was listing these terms. So a sequence is just, we talked about how it's just a set of integers produced by an nth term. The difference between a sequence and a series, this is a sequence, but if we now start to add all of these terms up, that changes it over from a sequence to now what we would call a series. So an infinite series is the sum of the terms in your sequence. So whenever we hear the word series, it means that we are finding the sum. That's why you're going to see this sigma notation here. From 1, since it's an infinite series, from 1 through infinity. So if it's an infinite sequence of terms, we add up all of those infinitely many terms together. Those terms are still created by our general term here, whatever that is, a sub k, a sub n, however we would write that. But the sum of that is our infinite series, okay? So the numbers a sub 1, a sub 2, a sub 3 are the terms of the series. A sub n is your nth term. It's how we're getting all of our terms. And then the partial sums, our first sum would just be the first term. The second sum would be the sum of the first two terms. The third sum is the sum of the first three terms, so on and so forth. So that ultimately what we would want is the sum of all of our terms would be from 1 to infinity. The sigma sign tells us we are adding up all of the general terms that we are going to be, that creates the terms in our sequence, starting with, in this case, 1 through all the integers through infinity. Okay? Similar to sequences in series, these can converge. So if our sequence of partial sums has a limiting value, we would say that it converges to that sum. If the series does not converge to a finite sum, then we would say that our series would diverge. Okay? So similar, but now we're just adding up what we were doing in the previous lesson. First four, identify if the following series converge or not. So we'll be pretty thorough with these first few so you understand what's going on here. The first, so if we kind of go up here where we talked about the first sum, second sum, third sum, so on and so forth. My first sum is just 1 because it's just the first term, going to be a 1. If I want my second sum, now I'm adding up the first two terms, which is going to be 0. The third sum is the first three terms added up, which bounces us back to 1. The fourth sum would be the first four terms added together, which is 0. And then we should see our pattern at this point. Our sixth sum would take us back to 0, so on and so forth. So very much like yesterday, in order for our series to converge, these should be approaching a limiting value. And like yesterday, when we bounce back and forth, in this case, we're bouncing back and forth between 1, 0, 1, 0, 1, 0. What that is telling us is we aren't converging upon anything. This series would then diverge. Okay? So similar to yesterday, we're just doing it now with their sums. So for number 2, if I wanted the first sum, that would be 3/10. I'm going to write that as a decimal. I think it'll be a little bit easier for you to see. The second sum then would be the 0.3 plus a 0.03, so that would be 0.33. The third sum would be the 0.3, 0.03 plus a 0.003, so now we're at 0.333, so on and so forth. Okay, so what we can see here now is if I go to the fourth term, we could all probably anticipate that being 0.333. We get another decimal with a 3. What this is telling us is this would be converging to a sum of 1/3. Okay, so that one converges. 3, first sum would be 2. The second sum would be 2.666. 0.666, so on and so forth. The third sum, know that 2/9 is 0.2 repeating. So if we were to kind of add all those up, now we're going to do 2 point, hold on, okay, I'm back. Sorry, had another kid issue. So this is 0.222 getting added on to that second sum. So now we're at like 2.8888 forever and ever and ever. If we go ahead and add that fourth term in here, so the 2/27, it is not nice pattern like we had before. It's 0.074, 074, so on and so forth. When we add all those up, we would get a sum of 2.96296, so, you know, it kind of follows that pattern. What we would hopefully then see is, as we're adding more and more and more terms, what we should be converging to is a sum of 3. Okay, so this one also converges to 3. This one up here was converging to 1/3. And then last one here, before we try and shorten this up a little bit, first sum would have been 1. Second sum, we add the first two terms together, -1. The third sum, we're going to add these together, -1 and plus another 4 is 3. If I do 3 minus an 8, it's a -5. Let's go ahead and graph this one real quick so it's kind of obvious. My first sum was 1. My second sum would have been a -1. My third sum we said is 3, so that's going to be up here. The fourth sum is going to be a -5 down here. So what we can see, this is kind of similar to what we did yesterday when we graphed them. We're bouncing back and forth, but we're not converging upon anything. So this would be one that we say diverges. Okay. I forgot in number 2, let me create a little bit of space in number 2. Let me get rid of this. Clear this out of here. I wanted you to write the formula for this. That would be something that we would want to be able to do. So write a formula for the series that we just got done with. That's what this is asking us to do. So we would definitely do our little sigma sign, although we don't necessarily need it. It's not asking you to write that. Yeah, let's not do that. We just want the formula. How are we getting all of those terms there? And basically what we are doing is we started at 2. Try that again. Move this down a little bit. There we go. And what we would be doing is starting at 2. And then what we're pretty much doing every single time is multiplying by a 1/3. So it's 2, and then we're going to multiply by a 1/3. So if our and there's different ways we can write this. Let me throw that out there as well. Actually, you would have done this quite a bit in Math 1, where we would have talked about, you know, do we want this to be an n or do we want this to be n minus a 1? So there's a lot of different ways that we can go about this. Since I called this s sub 1, then that's going to say that my n is a 1. And if n was a 1, then we would have gotten 2/3 as our first term. And that's not what we had. We had that. So it's probably one that we would want to put as a minus a 1. So that if we go ahead now and test this, plug in your 1, we would get 1/3 to the 0 power, which is a 1. Multiply that by 2, that gives us this first sum. If we went ahead and plugged in 2, 2 minus 1 is a 1/3. And then we'd multiply that by 2. We're going to multiply to get... All right, sorry, I'm confused. I'm distracted. Let's try that again. My bad. So definitely converging to 3. So that's not going to change. We're writing a formula. So let me clear some space here so I don't confuse myself. A lot of stuff going on at home right now. These kids. We're writing a formula for this. Okay. So what we would, again, start with is how do we start with 2? And then our next term would have been 2/3, 2/9, 2/27. So what we're finding is the sum. I'm going to go ahead and say that my first one is a 1. We're going to go to infinity. And then how would we get a 2? 2/3, 2/9, so on and so forth. So like I was writing, we started with 2. And then what we would then be multiplying by is 1/3 every time. So we're multiplying by 1/3 from 2 to 2/3, from 2/3 to 2/9, 2/3 to 2/10, or 2/27. So we would then raise that to the nth power, and then we kind of get into what I was talking about. If we plugged in this 1, which is what this is telling us to do, then n equaling a 1 would give us 2/3 as our first term, so that's not our first term. Our first term was 2. So we do one of two things. We say we can do n minus a 1. Then if I plug in a 1, I would get 1/3 to the 0. That's going to be a 0 or a 1 multiplied by that 2. We'll get 2 as our first term. If n is then a 2, we plug that in, we get 1/3 times 2, we get our 2/3. So that's one way that we can solve that. We also, and then depending on what we're doing, having to write these yourselves is a fairly common practice in this chapter, although we probably won't be doing that quite as much with not having to go over all of this now. Get rid of this. Gosh, just erase, would you? If we could erase, you know what, I'm not going to erase it. We could turn this into a 0, and then that's going to take care of our formula. Then we don't necessarily need now that. So if n is a 0, now this is a 1, we start at 2, and then we start multiplying by 1/3. Okay. If I ask you to rewrite this one, so let's go up here, and what this really is just a 1 negative raised to the nth power, because we're multiplying by a -1 over and over and over and over and over again. Okay. This you would have dealt with extensively. This is probably one of the things in Math 1 and Math 2 now that's better than before. Understanding the idea of geometric versus arithmetic. A geometric series, these are all geometric series if you remember, because geometric series tells us that we're multiplying by the same r over and over and over again. The reason we use r is because it's a common ratio. So in all 4 of these, if I ask you what was our common ratio in all 4 of these, if we look back in number 4, our common ratio was a -1. If we look in number 2, our common ratio was 1/3. In number 3, our common ratio, I'm sorry, I got that backwards here. Number 2, our common ratio was 1/10. This was our 1/3. And then in number 4, our common ratio would have been, what are we multiplying by over and over again? -2. All right. So geometric series, we can kind of look and see some of them are going to converge, some of them are going to diverge. But these are our common ratios. So for a geometric series, if we look at this now, we just see here's our first term, and then we take our first term, multiply it by our common r, multiply it a second time by the common r, a third time by the common r. Okay, this is our sum of a geometric series. A geometric series will converge to the sum of this. And then change this little marking. Notice how a is the first term. So this is the first term in our sequence of numbers divided by 1 minus your common ratio. It will converge to this sum if the absolute value of our ratio is less than 1, but it will diverge if the absolute value of our ratio is greater than a positive 1. So now let's test those first 4. If we look up here at number 1, so remember how number 1 diverged. The reason that diverged is because if we look at this little statement here, here is our r. If I took the absolute value of the ratio in number 1, its absolute value was a positive 1. And if our ratio is greater than or equal to 1, the absolute value of that should diverge, which it did. We should converge if our absolute value of the ratio is less than 1. So if we look at number 2 and we look at number 3, notice how each of those converged. And it is because the ratio of 1/10 and 1/3 satisfied this inequality. Its absolute value was less than a 1. If we then go to the final one, number 4 diverged. And the reason that it diverged is because if we look at this one and we do our absolute value, the absolute value of our r was, if we again focus here, was greater than or equal to 1. that's going to tell us that our geometric series is going to diverge. So what we get into a lot is what's called an interval of convergence. And for our interval of convergence of a geometric series, our common ratio has to lie between a -1 and a +1. Okay, so that's important. That's a big takeaway for the day. All right, so if we go to the series of problems now, it says determine that the following series converge or diverge. If they converge, state the sum of the series. If they diverge, state that it is divergent. And then also we would want to state an explanation why. Okay, so for this series, if we look at this, we're going from 2 to 2/3 to 2/9 to 2/27. What we would want to identify is what is our common ratio. What we're multiplying by repeatedly is 1/3. This actually is problem up here, number 3. We've already done this. This should converge to a sum of 3 because we actually kind of wrote all those partial sums out and we were able to see that they were adding all up to be 3. So now, our little shortcut that we talked about, we now have a formula for this. Whatever our first term in the series was, divided by 1 minus our ratio, should give us the sum of the series. And the reason we know it's going to converge is because our ratio was 1/3 and that absolute value was less than 1. Okay, so our sum for this problem should be our first term of 2 divided by 1 minus the common ratio of 1/3. So we would end up with 2 over 2/3. If we, dividing by 2/3 is multiplying by the reciprocal. So if we go ahead and do that, we end up with 2 times 3 over 2. Those are going to cancel, and we find that we were in fact converging to a sum of 3, just like we saw when we wrote out all the partial terms in number 3 above, or at least on the previous page. Okay, so number 6 should converge. This problem we have also done. That is number 2 that we talked about, where we just wrote out all the partial terms. We were able to look at them and see that we should be adding up to 0.3 repeating. So if we now look at this, we would be able to look at this here and identify that from 3/10 to 300 to 3/1000, our common ratio was 1/10. The absolute value of that is less than 1. That guarantees that this geometric series is going to converge. And our sum should be the first term divided by 1 minus our common ratio. So for this problem, our first term was 3/10. We would divide that by 1 minus the ratio of 1/10. So that leads us to 3/10 divided by 9/10, which is the 10s would cancel, 3/9 for a sum of 1/3. Same thing that we saw when we did our partial sums earlier. Okay. Number 7 now, you just have to be really careful with this, because if you don't recognize that our ratio is a -2 and the absolute value of that is greater than or equal to 1, and we know right away that this diverges, then it's easy to get this wrong, because you can definitely use this formula and say that the first term divided by my ratio, this will give you a number. We could plug in a 1, and then we would do 1 minus, and our common ratio is a -2. That'll definitely give you a finite number, and you might think that you're converging to a 1/3. But when we did this earlier, all right, that was number 4 here, we can see that these guys are diverging. We're not converging upon any particular value. So we have to recognize right from the get-go this part of it here, so that we never get to this part. And we can say right away that that's going to diverge. Okay? So now, the rest of the problems you haven't seen before, but it's the same setup, the same process. So if we look at number 8, what we would identify hopefully is I went from pi over 2 to pi squared over 4 to pi cubed over 8. So our common ratio would be pi over 2. All right? Absolute value of this is greater than or equal to 1. So this guy diverges. Then the explanations in this, and this is some of the stuff we're skipping, which is nice because this is one of the major hangups that people would have. But whenever we make a divergent statement, we've got to explain why. So the way this is going to be written is we would say that this is a geometric series. So if we are back for a quiz, this would definitely be something you would need to be able to do. This is a geometric series with a ratio, absolute value of our ratio, equal to pi over 2, and that is greater than or equal to 1. That is how that statement needs to get written. All right, we state that it's a geometric series. The absolute value of our ratio is pi over 2, and that is greater than or equal to 1. That's our proof, evidence, statement that would show that this series diverges. Okay? All right, number 9. Notice in 6, 7, and 8, I actually write out the terms. The rest of these, I don't write them out. I just give you the general term. So as you're getting used to these, and eventually we'll be able to look at number 9 and do this right away. But as we're just getting started with these, I would strongly recommend just writing out the first few terms of these and then identify what's our first term and then what's our common ratio. So if I started an n value of 1, I would get a negative 1 to the 0 power. I would get 4 to the 0 power, so that we would know our first term is 1. And then we're going to add that. Let n be a 1 now. So now I get a negative 1 to the first power, and then 4 to the first power. So that's my second term. Plus, let n be a 2. I would get a negative 1 squared, so that's a positive 1. And then 4 squared is 16. That's usually enough. 3 to 4 should be plenty for us to identify what our pattern is. So what we would hopefully recognize now is that our first term is 1, and our common ratio is a negative 1/4. This is a good ratio in terms of us converging because the absolute value of this is less than 1. So this should allow our series to converge. So we can go ahead with our whole sum is the first term divided by 1 minus our ratio. The first term was a 1. And then I do 1 minus a negative 1/4, which is 1 over 5/4. So our sum would be 4/5. So we are converging to 4/5. All right, we should probably write it that way. So converges to 4/5. 10. I'm going to write out those first few terms again. If n is a 1, anything to the first power would be a 1. If I let the n value be 1, now I get 3/5 to the first power, so that's 3/5. If n is a 2, I would get 9/25, so on and so forth. So what we should hopefully then be able to identify is our first term is a 1. And to go from 1 to 3/5 and then 3/5 to 9, our common ratio is 3/5. That is a ratio whose absolute value is less than a 1. So we should have a sum. This will work. First term is 1. 1 minus our common ratio of 3/5. And what is that? 1 over 2/5 for a sum of 5/2. All right. Next one. Let me get a little eraser here. Come on. First term, if n is a 0, negative 1 to the 0 would mean we have a positive 1. And then I get 5 over 4 to the 0. So this first term should be 5. Recognize what this negative 1 to the n does. We've seen this now a few times. That should alternate our signs. If n is a 1, we get a negative 1. So we're going to get minus. And then I would get 5 over 4. If n is a 2, now I'm going to be positive 1. Negative 1 squared would be positive. And I would get 5 over 16. So what we would see is our first term 5. Common ratio is a negative 1/4. We're multiplying each term by a negative 1/4. Absolute value of that is less than a 1, so we can go ahead with our sum. First term over 1 minus the ratio. First term is 5. Our common ratio is a negative 1/4. So we end up with 5 over 5/4. So our sum is 4. So we are converging to 4. Sorry, this is getting messy. Not easy to write with this pen. It's kind of big. 12 is a big one. This is one that if we quiz, there is one like this on the quiz. People tend to mess this up, even though I'm going to show you right now what to do. So just make a note of this. Make sure we understand how this plays out. I'll keep this short. Sometimes if we have time in class, but I won't keep it too long on a video. I actually write out like if I let n be a 0, my first term is 5 over 1 plus 1 over 1, and the first term is 6. And we write out the first 3 or 4 of these, and what we find is this is not geometric at all. We don't have a common term or a common ratio that we're multiplying by. And we talk about that a little bit. But then we ultimately get to what we want to do, need to do, is we really need to split these up. So we want to do one as a general term of 5 over 2 to the n, plus the other one with a general term of 1 over 3 to the n. Then if they both converge, we would add those results together. If one of them diverges, then obviously it doesn't matter that the other one has a sum. They would overall have to diverge. Okay, so we treat this as two separate little problems. So we'll write out the first few of the first term. So take your 0, plug it in. The first term for this one would be 5. If n is a 1, I would get 5 halves. If n is a 2, I would get 5 fourths. So that's the first one. Okay, so let's keep this isolated. Then we're going to add that. Write out the first few terms for this one. If n is a 0, I would get 1 over 1. If n is a 1, I get 1/3. If n is a 2, I get 3 squared, so 1/9. So this one has a first term of 5 and a common ratio of 1 over 2. So this one is good. This has a ratio whose absolute value is less than a 1, so this sum will converge. Over here, our first term is a 1, and its common ratio is a 1/3, which means this one would also converge. So what we need to do then is find the sum of both of them, and then since they were joined together by a sum, we would add up those two results together. Okay? So let me try to squeeze this in. So my first sum would be this first term of 5 divided by 1 minus 1/2. So this is 5 divided by a half. This has a sum of 10. The second sum, first term is 1, and then I would do 1 minus 1/3. So that's what, 1 over 2/3. We have a sum of 3 halves. So we would add those together. All right, 10 plus 3 halves. So that means that this is converging to 23 halves. All right, so if they're separate or two separate terms, make two separate problems out of them, find each individual sum, add or subtract them based upon what this symbol is telling you that you need to do. All right. Okay, 13. We have root 2 to the n, so that would be our initial term would be root 2. Root 2 squared is 2. Root 2 cubed would be a root 8, so 2 root 2, and we continue to multiply by root 2 over and over and over again. This is one that we have to recognize. Even though our first term is a root 2, our common ratio is also a root 2. That is greater than 1. Hopefully we know that. Whew, excuse me. So this is one that we would say diverges. And then we would say, let me not write so large. So this one diverges, because these explanations are important, and it's what sometimes causes some issue, because we have a geometric series with a ratio whose absolute value is equal to root 2, and that is greater than 1. All right. All right, I wrote very large over here, so let me clear some space for you. 14. We want to recognize what 14 is. It's a little different way to show an alternating series. So when you see the little -1 to the nth power, that's pretty obvious. We're going to bounce back and forth between positive, negative, positive, negative, positive, negative. That's the most obvious way and the most common way that you're going to see that. But this is another way. If we look at the cosine of n pi, if you let n be a 0, you get the cosine of 0. So you're going to get a 1. And then over 5 to the 0, which is another 1. If n is a 1, though, you're going to get the cosine of pi, which would be a -1. And then 5 to the first would be a 1. plus. If n is a 2, cosine of 2 pi is a positive 1, and then 5 squared would be 25. So this also gives us an alternating series, positive, negative, so on and so forth. So that's something you want to be aware of, just so we don't get tripped up by that anytime in the near future. We see in this one, first term is a 1, common ratio is a negative 1/5. That one is okay. Absolute value of negative 1/5 is less than a 1, so we're good. So our sum should be the first term of 1 divided by 1 minus the common ratio of a negative 1/5. So that's 1 over 6/5. So this one converges to 5/6. Okay? So that's kind of our first way to determine if a series converges or not. If it is geometric, which means we have the same number being multiplied over and over and over again, we know that it converges based upon the value of our r. Okay? Oh, I guess we have one more. Sorry, I thought we were done with those. This one we've already done. On the first page, if n is a 1, you're going to get a negative 1 for the first term. Then we would get a positive 1, negative 1, positive 1, negative 1, so on and so forth. And what we see here is our r is a negative 1. And because the absolute value of this is equal to a 1, this guy would diverge. Oops. And we would say it's a geometric series. With a ratio whose absolute value is equal to 1. All right. The next thing to determine if a series would converge or diverge is what we call the nth term test. So it says an obvious requirement for convergence is for the last term, and the last term is our nth term. That last term must be approaching 0. If it does not approach 0, then the sum would always be getting larger and larger and larger. Therefore, the series would have to diverge. So the nth term test is telling us that if we're given a series, so here is our series. Notice this is a regular old a sub n, doesn't necessarily have to be geometric. This series will diverge, and the nth term test is only something that would prove divergence. We know a series will diverge if the limit of our general term fails to exist. So basically what we did yesterday, if we found the limit of our general term and we get like a D and E, or if that limit fails to equal 0, our function would have to diverge. Okay? So let me go to, I'm going to go to number 2 first, because I think it's the one that explains this the most clearly. Notice number 2 is not geometric. If we wrote out the first few terms, plug in a 1, you would get 2 over 1. If you plug in a 2, 3 over 2. And if we plug in an n value of 3, we would get, 4 over 3. There is no common ratio here. So now that we've done geometric series, don't think every series is going to be geometric. All right, that's not the case. So what the nth term test is asking us, or telling us that we should be able to do, is basically, don't necessarily do this on yours. Let's pretend this wasn't a series. So basically what we did yesterday in yesterday's notes. This is our nth term test. So this is our a sub n. So our a sub n in this problem is n plus 1 over n. If we go ahead and find the limit of this, so let's turn this into a limit and find the limit as n goes to infinity. The limit of this is 1. The degrees are the same. Look at their coefficients. The limit is a 1. So here's where you have to keep these two items straight. Yesterday, so in the previous day, when we were doing 8.1, as long as it went to any finite number, this sequence would converge. So eventually what that is telling us is basically every term in our sequence becomes a 1. As we go to 1,000,000, 2,000,000, you pretty much get a 1 over and over and over again. So yesterday, that's good for convergence. Today, that is a problem, because what we are doing today is we are taking this little sigma sign. So if you remember what the sigma sign means, that means we are adding these together. So if every one of our terms is a 1, think about what that would mean if we're going to add 1, add 1, add 1, add 1. Wouldn't that tell us that our series is continuing to get larger and larger and larger? That is why not only does this limit have to exist, so if we went back and talked about our limit, so this limit did exist. Come on. The limit was a 1 for this sequence, but the only way that our series could converge is if it equals a 0. This has to be going, these have to be turning into zeros in order for the series to converge, okay? Hopefully that makes sense. This gets tricky really quick, and a lot of it is based upon that idea first and foremost as we move along through this chapter. So in this case, what we would say is this diverges because what we would call the nth term test. So we would write this out, nth term test. And what we would say is the limit as n goes to infinity for our general term is 1 and not the 0 that it needs to be. All right. Let's revisit number 1 now. If we were to ignore this fact that we're adding all of these terms together, this general term from yesterday, if we found our limit as we go to infinity, this has to equal 0. It has to exist, and it has to equal 0. Well, this one's kind of the easiest. It's a little easier than number 2, but I think 2 makes the most sense. As n goes to infinity, this guy would have a limit of infinity. It just gets larger and larger and larger and larger. So this limit doesn't exist. It exists, it just doesn't equal a 0. So this would have to diverge. So we would write that it diverges. Nth term test. That the limit as n went to infinity for the general term was infinity and not the 0 that it needed to be based upon the nth term test. Okay. Number 9, a couple different routes we could take here. What just happened? A couple different routes we could take here for based upon the nth term test. So by a couple different routes, just look at number 15. So these are the exact same problem. So one of the things we could do, we've already done. We could say that this diverges because it's a geometric series with a common ratio whose absolute value is a 1. That's one route we could take here. Or we now have a different way of justifying this, and that would be that this would diverge based upon the nth term test. That the limit as n goes to infinity for our general term does not exist. So if we had done this yesterday, which we did do something like this yesterday, and just worry about what happens here, this just bounces back and forth between 1, -1, 1, -1, 1, -1. That limit would not have existed. And because of that, it fails the nth term test. If a sub n fails to exist or not equal 0, then it would have to diverge. And this one fails the nth term test because it doesn't, or because the limit doesn't exist. 4, pretty much the exact same thing. What we just talked about earlier. This is another way of basically saying a -1 to the nth power. We're going to bounce back and forth between 1, -1, 1, -1, so on and so forth. So we could, again, do what we did up here and say that this is a geometric series, or write the same explanation that we just wrote, that this diverges, nth term test, the limit as n goes to infinity for our general term does not exist, and it has to exist. All right, 5, let's see if we remember this from yesterday. So maybe pause me, see if you can actually do this one. This one is a little review from yesterday. First and foremost, recognize our little pattern here. This is one we might want to rewrite. So natural log n over n is a 1, and then I would have 2 over n, and then all to the nth power. So again, yesterday we didn't worry about this. So we weren't concerned about it being a sum. So this is one of our little tricks yesterday. The big trick yesterday really is recognizing that, let me get rid of all of these things for right now here, that what this is, we would have said yesterday that this converges to e squared. Today we have a natural log in front of this. So as the inside becomes an e squared, we would ultimately be taking the natural log of e squared, so that overall the general term converges to 2. But that was yesterday. What this means is every term is basically a 2 as we go to infinity, and we'd be adding 2 over and over and over and over again. So for the sake of a series, the fact that we are again adding because of the sigma sign, if we continue to add 2 over and over again, our sum is going to get larger and larger and larger. So this guy should diverge. All right, let me create a little space here so we can write our explanation. So this diverges from the nth term test. The limit as n went to infinity for that general term was equal to 2, which is not the 0 that it needs to be. Okay. All right, 6th, last but not least, there are 2 ways we can now do this guy. So hopefully we understand it. It's why I put this one last, so that we can tie these 2 things together. This is a geometric series. So our first term would have been 3 halves. Our second term would have been, what, 9/4. Third term would have been 27/8, so on and so forth. What we would see is our r is 3 halves. That's what we're multiplying by repeatedly over and over and over again. So because of that, this would diverge because of the nth term test. Limit as a, my bad, that's not what we're talking about. That's number 2. What we just showed is it diverges because it is a geometric series with a common ratio whose absolute value is equal to 3 halves, and that is greater than or equal to a 1. So that's one option. I kind of already gave away the second option. Let me create some space here. So think back to the last few days. I'm going to rewrite this little expression as 3 to the n over 2 to the n. What has to happen for the nth term test is our limit has to equal 0. So if you think back, if I ask you which of these 2 functions, 3 to the n or 2 to the n, grows faster, the exponential function with the greater base is going to grow faster. So the fact that this has a 3 as the base and this has a 2 as the base, that tells us that this function is growing faster. Well, if that function is growing faster, then what that would tell us is, if I ask you to find the limit as n goes to infinity, our limit would be infinity. So because of that, it would diverge due to the nth term test. That the limit as n went to infinity of our general term was infinity, and then that's obviously not the 0 that it needed to be. Either one of those justifications would be totally fine. The choices are what get crazy. That is something that the AP test has taken out. There's a bunch of ways that we can kind of go through this, but that's something that you want to really keep straight. It's one of the things that really trips people up in this section. So that's a wrap on that. If you have any questions, you really want to stay on top of this. Hopefully we will see you next week. So if there are any questions, we can take care of this. But as we're moving through this chapter, you want to be really, really careful, because things can get pretty wild and crazy pretty quickly. So if you start getting tripped up, please reach out. I'll do my best. We can Zoom at some point. I'll probably throw a Zoom review up where I can try to explain things a little bit better. You can ask questions real time, and hopefully we can figure it out. So again, I appreciate everybody's time and effort. I know this is not ideal. Keep working hard, keep doing your best, and hopefully we'll see you guys soon.